Good afternoon. 2 p.m. Kiev time, and we start our second session. And I invite the chairman of the session, please, Natalia. I would like to introduce you. Thank you. Please switch your phone.
Okay. Can you hear me?
Yes.
Yes.
Okay. So good afternoon. My name is Natalia Litchinitser. I'm from Duke University, and it's my pleasure to introduce the first speaker, Professor Porras, who will talk about observation of natural Stokes Skyrmions in optical vortices.
So, can you see my screen?
Yes.
Yes, thank you. So, thank you very much for inviting me to this conference, very important conference. And even if I am not an expert in singular optics, but I have been helped by my colleagues to understand all very interesting features of light. I'm going to talk about the different new type of Stokes Skyrmions that are naturally present in optical vortices, and also on their non-diffraction propagation invariant, no? And also that they are confined in a tube of very, very small radius, sub-wavelength radius. This is a joint research with my colleagues and students, Mata-Cervera, Deepak Sharma, Ramon Paniagua-Dominguez, and Shen from Singapore and Spain in different universities, the Technical University of Madrid, the Nanyang Technological University, the A-Star in Singapore, and the Spanish Research Council in Spain. So to start, first, I would like to I don't see my own screen because the control bar, I don't know how to shift. Okay. Next one. What happens? Sorry. Sorry. First, I will describe these skyrmions that address the phase singularity of optical vortices and their experimental observation. Second, I will show you their subwavelength confinement in a tube for radius that is controlled by a kind of a spin-orbit coupling. Third, I will talk about the non-diffraction propagation or propagation invariant property of these skyrmions. So, this is, just to start, an optical vortex embedded, for example, in a Gauss beam. This is the phase, and this is the amplitude or intensity. And it has a uniform polarization state. It is what is called a scalar beam. For example, the polarization may be linear, maybe elliptical or circular, left-handed, right-handed. It is not important. The important point is the transverse polarization is more or less or locally uniform. So, but this is not, of course, a complete description of the electromagnetic field because we have, according to Maxwell equations, particularly Gauss divergence equation, we have an axial component, usually very small. It can be evaluated, for example, with this formula for the transversal components, or this simple formula in the paraxial approximation or paraxial propagation. And then, taking into account the existence of this axial component, when we examine the close vicinity of the vortex of the phase singularity, we observe a quite rich transverse polarization, axial polarization texture, which is in fact a skyrmion of the Stokes vector. I recall what is known previously, which are Stokes skyrmions or standard Stokes skyrmions, also called Skyrmion beams. In them, the full Poincare sphere, the Stokes vectors in the full Poincare sphere of all transverse states of polarization are mapped in on a transversal plane. For example, the well-known full Poincare beams that display all possible transverse states of polarization in a transversal plane. And we also have the Skyrmion number, which measures the number of times that the map wraps the Poincare sphere. The Poincare sphere. These Stokes Skyrmions typically are constructed by superposing two modes of propagation, for example, a Gaussian beam and a Lagrange Gaussian beam of azimuthal order L, for example, with orthogonal states of polarization, left circular left-handed and right-handed, orthogonal states of polarization. In this particular case, the Skyrmion number, the number of times that this map wraps the sphere, or vice versa, as you like, is equal to the azimuthal order or topological chart of the vortex. Somehow, I can say that these Skyrmions, in contrast to ours, are constructed somehow artificially in some way, no? Because we have to perform this superposition. In contrast, all optical vortices, as I tell more detailed later, carry naturally a Stokes Skyrmion in their core close to the vicinity by virtue of the Gauss divergence law. In some sense, they are universal. We observe here that when approaching the singularity, the phase singularity, which is here, we pass from pure transversal polarization to pure axial polarization, with all inclinations of the polarization ellipse in the path. Also, rotating around the singularity, all azimuthal orientations of the polarization ellipse are present. So this is quite different because it's a Stokes Skyrmion of transverse axial polarization. In fact, if we define Stokes vectors and normalize Stokes vectors, but of transverse axial polarization, but the definition is the standard. We don't write here X and Y, but write transversal polarization and axial polarization. We can construct a Poincare sphere of transverse axial polarization, representing all possible states of transverse axial polarization with, this is important, not all possible states of polarization, of course, with the given transversal polarization, which may be circular, elliptical, or linear. Important point is that the antipodes are always orthogonal. So, for example, if we with decreasing latitude in the Poincare sphere, we pass from pure axial polarization to pure transversal polarization, and it is mapped from the phase singularity towards the periphery. And with varying latitude, longitude, for example, from one meridian to another meridian, we have all possible orientations, azimuthal orientations of the polarization plane of the polarization ellipse, and they are mapped surrounding the singularity. So these natural Skyrmions, okay, I forgot that it's important, but sorry. The Skyrmion number of them is different from the standard one because it is just the sign of the topological charts, the sign of the topological charts of the vortex. And we have here a polarization singularity. So we have a phase singularity and also a polarization singularity in the same place. This is what is called a set point, different from C points or L points, V points, and this is a singularity with undefined azimuthal orientation of the polarization plane. So we have observed these Skyrmions. It is not at all easy because the axial component is usually very small in comparison with the transversal components. So we have to enhance it by focusing, and we have, in principle, two options: non-paraxial focusing or paraxial moderate focusing of some fields that we know that have an enhanced axial component. We have chosen this option, the second option, using focusing a uniform beam with a punctual vortex, like this. The amplitude is uniform initially. topological charge 1. And this is our experimental setup. For the observation, initially we prepare here left-handed circular polarization. And instead of using a lens, we have used this meta-surface that has three functions. The meta-surface converts completely, almost completely, to right-handed circular polarization, shapes the vortex phase, the azimuthal variation of the phase, and with an uniform amplitude, and also focuses it. We don't need a lens because it is imprinted here in the meta-surfaces. And we want to observe the Skyrmion structure here at the focal plane, which is easier because the axial component is stronger. So we have imaged the focal plane into our camera, and in the possible residual left-handed circular polarization is removed with this filter. And using the interference fringes with a reference beam extracted from the initial one, we can reconstruct the complex transverse field, the X component and Y component, the amplitude and the phase. And from it, the transversal component, we can evaluate also the axial component from divergence law, for example, using this formula here. And you can see here the results at the focal plane. This is a theoretical simulation, and this is from the experiment. The first column is the transversal component. The second column is the axial component. We have also the amplitude or intensity and the phase with the vortex, etc. And this is a Y slide just to show you that the axial component is not very small, but is significant, about 50% the value of the peak value of the transversal component. What else? And here, from the transverse component and the axial component, we are able to evaluate the transverse axial Stokes vectors, and from them the latitude and the longitude. And this is the theory, and this is the experiment, which is very, very similar. And we see that the whole transverse axial Poincare sphere is covered, except for some uncertainties in the experiment. So, in short, in this first part, we have made observable this different type of Stokes skyrmion called natural skyrmion with the predictive features. This is the first part of this work and a kind of preliminary summary. Just to say that until today, skyrmions in optics, particularly Stokes skyrmions, are constructed rather artificially with that superposition. Okay, it's good, but this is different. We have unveiled the existence of an optical skyrmion that is carried naturally by optical vortices according to Maxwell equations. This is the idea. And we have published these preliminary results in this paper. But fortunately, these natural skyrmions have other interesting properties that I will try to tell in the second and third part of this presentation. So how big is this skyrmion? How wide in the transversal plane? So the skyrmion number, we have to integrate. Theoretically, we have to integrate over the whole transversal plane, r approaching infinite, to have integer skyrmion 9. This is the same situation as with full Poincare beams. We have to integrate over the whole transversal plane to have a skyrmion number equal to L, no, or unity. But in practice, convergence to integer skyrmion number is very, very fast in a few wavelengths. For example, if we integrate on this radius, we cover this part of the Poincare sphere. If we integrate over a larger radius, we map almost the equator of the Poincare sphere, and for in about 2 wavelengths, we cover the almost complete Poincare sphere. As a criterion, for example, we have 99% of the Poincare sphere covered in this radius that we call skyrmion radius. Its particular value for different polarizations, transverse polarization, and different optical vortices topological charge depend on a mysterious orbital spin angular momentum coupling. spin cap angular momentum associated to the transversal polarization. 1 for right-handed circular polarization, -1 for left-handed circular polarization. So according to this formula, the radius is maximum with maximum spin, circular polarization, parallel to the orbital angular momentum, with a radius of about 2 wavelengths. And we have minimum radius falling down to 0 for maximum spin, for example, circular polarization, and anti-parallel orbital angular momentum. In that case, the radius, according to this expression, approaches 0. In this experiment that we can see here, we have fixed this topological charge, +1, and we have changed the spin from right-handed circular to left-handed circular, and we observe that, in fact, the Skyrmion rank from the maximum value to almost 0 radius. So this is the first interesting property, the subwavelength confinement. And the second one that we realized very recently is sorry, the propagation invariant property that we can call also non-diffraction propagation of these natural Skyrmions. So this subwavelength confined Skyrmion is exempt from diffraction effects, diffraction spreading. It means that it propagates forever, reaching even the far field without any change in size and shape, even if the nesting vortex beam, the Lagrange beam, for example, experiences diffraction spreading, as you can see in this conceptual figure. This is the Skyrmion tube, and this is the Lagrange beam spreading. And this touches another problem, traditional problem in optics, that is non-diffracting propagation or diffraction-free propagation. This traditional problem has been investigated for more than a century, and all attempts or advancements have always led to somehow ideal waves, such as airy beams, Bessel beams, all then carrying infinite power. This is the idealization. And their physical realizations at the end eventually always diffract. So they can call their physical realization quasi-non-diffracting or pseudo-non-diffracting beams. Here it is another perspective. It's quite different, but of course, we have found a real-world light wave structure that doesn't involve issues with finite infinite power that propagates without spreading, without its propagation invariant. It's a propagating light structure. Let me recall, of course, I know you know perfectly what's diffraction, of course, but let me stress some aspects. No, diffraction is not only a spreading of the intensity pattern, as you can see here, this airy pattern, for example, no, but also all features in their ever-divergent wavefronts separate apart. For example, these two zeros of the intensity pattern separate as they propagate up to the far field, and also the polarization features, which we have here. Sorry, a linear polarization, circular polarization, and this polarization texture also diffracts. Also, all features separate apart. In fact, this happens with the standard Stokes Skyrmions, also called Skyrmionic beams. They experience diffraction, those constructed artificially by this superposition, and they diffract at the same rate. The polarization features, texture, diffract at the same rate as the composite modes do. It could be the same, of course, with our natural Skyrmion, but it doesn't. We don't know. But I can show you first theoretically and then experimentally. It is not difficult to demonstrate the non-diffracting propagation or non-spreading or propagation invariant propagation of these natural Skyrmions. This is a vortex, the azimuthal linear variation of the phase, and this defines a uniform polarization state. And it propagates, for example, according to Fresnel diffraction integral, this is paraxial propagation. We don't have formulas for non-paraxial, but paraxial is enough. This particular expression is for this particular type of light with a vortex, etc. This is the Bessel function of order L. And from an asymptotic analysis in the vicinity of the singularity, we arrive to this expression, which is well known. R rise to the topological chart and the azimuthal variation of the phase. Okay, it is well known in a focus, but not when the diffraction, when the wavefronts are diverging. It can be truly demonstrated this at any propagation distance. And according to this, the axial component given by this formula in the paraxial approximation is given by this expression. We observe here, interestingly, that the transverse component and the axial component both depend on the propagation distance, of course, no? Because the being is attenuated and spread. No? But we have evaluated this quotient between the axial component and the transversal component, and it doesn't depend on the propagation distance. This quotient completely defines the Stokes Skyrmion, the natural Stokes Skyrmion. It defines completely the transverse axial polarization texture. So, for example, this factor 1 over R provides all amplitude ratios of the axial component to the transversal component. And this phase here provides all phase differences between the axial component and the transverse component. So this quotient completely defines the previous I have talked about in the first part of this small talk presentation. And the important point, I repeat, is that it is independent of the propagation distance set. So even if the transversal component and the axial component, the skyrmion itself, its polarization texture, is independent of the propagation distance in shape and size. Of course, the power within it may diminish a lot when the beam is diverging, but can be increased a lot by focusing it. And this is the last part, which is the observation, experimental observation on the non-diffraction property of these Stokes skyrmions. It is quite similar with some differences with the previous experimental setup. Here we use a special light modulator, not the meta-surface, and it shapes a vortex of topological charge 1. And this quarter wave plate prints right-handed circular polarization. The whole story is focused, and we scan the focal region, now not only for the focal plane, but the focal region that it is imaged in our camera. And from the interference fringes from this reference beam, we can reconstruct, as before, the complex transverse electric field. I show it here just to see that we have scanned a quite considerable part of the focal region, about 2 or 3 Rayleigh distances, and we see diffraction of the Laguerre-Gauss beam or whatever. This is a Y slide, this is an X slide. And focusing is not too strong. In fact, it is paraxial because the spot size is about 11 wavelengths. So from the transversal components, we evaluate using Gauss divergence law, the axial component, and from it, we evaluate the transverse axial Stokes parameters and the latitude and the longitude, and they are plotted here. As a function of the propagation distance, we have that the full, as before, full Poincare sphere is covered. No? We have all latitudes and or longitudes, and we extract here some transversal patterns of the Stokes parameters at different propagation distance, and we observe that it is propagation invariant, so non-diffracting, even if this set distance is the same as this one. It doesn't change, being confined in about one wavelength, and this axial propagation distance is about more than 1,000 wavelengths. This is huge. For comparison, a normal beam will spread in about 1/10 of the wavelength completely, but there's a difference of 4 orders of magnitude. So I recall briefly that other non-diffracting beams structures, for example, Bessel beams, ID beams, and there are polychromatic generalizations, named sometimes localized waves, space-time wave packets, more recently, traveling at different groove velocities from 0 to infinity and so on, and even negative groove velocities. All of them are based, the non-diffracting propagation, on amplitude and phase shaping techniques, and in the case of polychromatic beams, on very specific spatiotemporal couplings performed usually in the frequency domain, between the spatial frequencies and temporal frequencies, and are to be truly non-diffracting. There are ideal waves that require infinite power or infinite energy. In contrast, the non-diffraction of our natural skyrmion, okay, this is a completely different point of view because we are this really in topology of light, no, in beam shaping and so on. But we have observed this possible solution or idea of solution of this problem of non-diffraction. All what we need is a vortex beam, which carries, of course, finite power. There are no issues with infinite power. I have recently, just today, I disappeared in archive. If you are interested on more details about this, and so as a kind of conclusions, in the first part we have predicted the existence and observed experimentally these different type of Stokes Skyrmions that are not constructed but are naturally present in optical vortices as demand the laws, the Maxwell equations. And in addition to the new topology, unique topology with different polarization singularity, they combine two properties sought from many decades. I could say from the beginning, from the invention of the laser, but I don't want to be too strong. But to the best of our knowledge, never observed together. Namely, the arbitrary self-wavelength confinement controlled by a spin orbit coupling, and second, non-diffracting or propagation, non-diffracting propagation of propagation invariant property without involving any idealization. So that's all. Thank you very much for listening.
Okay, let's thank the speaker, and the talk is open for questions. Any questions? Okay, let me start. I have a quick question. Very interesting talk. Thank you so much. My question is, in this non-diffracting skyrmion, if it propagates in non-ideal free space, but in, say, some scattering medium or something else, how stable it is if you looked at its stability?
Yes, we are investigating in this. We plan to investigate on the propagation not in free space, but first the self-reconstruction property, placing obstacles in the path on the propagation, no? And we expect to obtain a self-healing property for these skyrmions. And then the next step is the propagation in turbulent atmosphere or scattering media. And in a similar way, I think that this topology is quite stable. I don't know. I said at the beginning that it is not my expertise. I'm not expert in singular optics, but my students, which are very clever, sometimes more than me, say that they should overcome the scattering and the other problems with turbulent atmosphere. So our next research is about this point.
I see. Thank you. Okay, any other questions? Okay, I don't see any hands raised or anything. Okay, then let's thank the speaker again and move to the next talk.
Thank you very much.
Yeah. So the next talk is titled Stimulated Gravitational Lensing, a new laboratory astrophysics platform using complex light. And the talk will be given by Professor Galvez.
Hi, can you hear me?
Yep.
Okay, so I should hold on. Let me share my screen. And then let's do this. Okay, hold on. Let me, okay, let's share again. Okay, so now you can see the full screen, correct?
Yes.
Okay. Well, I want to thank the organizers for the invitation. Uh, uh, it is sad that we can't see each other in person. I've been attending conferences in Ukraine way back since the conferences in Crimea are organized by Marat Soskin and co-workers. And so anyway, I have a special fondness to these conferences in Ukraine, and I appreciate very much the organizers to continue this tradition despite all the challenges that they face. So I'm going to tell you about a project we've been working now for a few years, and so it involves scalar beams, which is somewhat of the departure of what we have been hearing. Very interesting work, of course. And this is a project that really started out of curiosity, which is um, how can we simulate in the laboratory gravitational lensing? And turns out complex light is right in there. Uh, so let me, before I get too far, let me tell you about the co-authors, a bunch of students. I have one that is currently at, at the university, but others have graduated. And then two postdocs, one has left already, and then the current one is Carlos Cardoso. And I'm going to show you some work that is oh, let's say, studied theoretically by colleagues at the University of Barcelona, Oleg Bulashenko and Anna Moreso-Serra. This work was also funded by the National Science Foundation of the US. Okay, so we've seen these pictures many times of um, pattern of stars and galaxies. And in there we see these arcs, and of course these arcs are a consequence of gravitational lensing, the deflection of light by the curvature of space. And this image was taken by the James Webb Space Telescope, and it involves 19 lensing situations. There's a cluster of galaxies in the middle that is seen, but I guess that the gravitational field is unseen only by these streaks that we see. And but now one of the challenges that we faced when we started doing this work was not that things were very unknown, but the opposite. Things were very known. Gravitational lensing is a mature field, and it has studied mostly the geometric optic limit. So among the findings of this field that really was worked on very intensely, let's say in the 90s, is that they show the presence of dark matter. Actually, that came much earlier, but then also they put a constraint on machos, which is what if the rocks, what if that dark matter are just dark rocks out there, and it was using gravitational lensing, it was shown that that was not the case. And then one has seen also the discovery of planets around dark bodies, and then even uh, it has been used to narrow the value of the Hubble constant because light is traveling through space-time, and that can be used to our advantage. Now, the what we can do in the lab, of course, with lasers, is to study the wave optics, and so then we have also the wave diffraction limit. However, in astrophysical observations, diffraction has never been observed, and that we can understand that because there's spatial coherence. The source may be a galaxy, of course, but, let alone a star, and so that you have spatial decoherence. And even if you have that spatial decoherence, you need almost perfect alignment because the light has a very small wavelength, and then when light gets lensed, just the light is traveling vastly different paths that are light years in length, or even hundreds or thousands of light years in length. And we're to get temporal coherence, we need that difference in path or in time of travel to be, or the wavelength or the frequency of the light. So it is just too challenging. However, uh, the situation might be different with gravitational waves because they have very large wavelengths, and the black hole mergers can act as point sources. So there's some interesting situations uh, that come up. So let me go over the ray optics of lensing. So you have a point source and then a lens. So then light gets deflected as it goes around this mass. Now, the, the what made me get into this problem was to hear or to read from articles of what is called the thin lens approximation. And that is that the distances from source to lens and from lens to Earth are so vast compared to the distance over which the light is bent uh, due to the curvature of space, then so that one can approximate that bending of the light to occur in just a plane. And then that's a thin lens approximation. So of course that means we can simulate that with a flat electro-optic device like that special light modulator. And so here you see the various rays, and then the deflection of the rays, which was predicted by Einstein, uh, is given by this equation. R is the Schwarzschild radius, which is the radius below which light cannot escape, say, a black hole. And m is the mass, and c is the speed of light. So then R is the impact parameter. Um, and if the rays are symmetric and we are in that unique situation where there's perfect alignment, we're gonna see rays coming from all angles, and then in that produces what is called an Einstein ring. So Einstein predicted this uh, to be of the order arc seconds. This was like in 1935. And a note that he made uh, about this work was, of course, there's not much hope of observing this phenomenon directly because in that time the resolution was not there. But of course, our astronomical instruments have improved much, and lensing has been observed. And here is a very nice example of an Einstein ring um, from this taken by the Hubble Space Telescope, and then here you can see that the ring is not a pure ring because the object is extended, is some galaxy. So so just for you to be get a little sense, the short shell radius of the sun is 3 kilometers, and and so we could do lensing with the space deformed by the sun, but we need to be at 550 astronomical units. The distance from the Earth to the sun is 1 astronomical unit. And then Pluto is at 50. The Voyager, the farthest satellite now from Earth is 160. So it'll be a challenge to do lensing with the sun at this point. So how do we image this in the laboratory? So we have a point source. Uh, so our lens is a spatial light modulator, and then uh, on Earth we are looking at different angles. So we need to put simulate that with an aperture and a lens and a camera. So and then here, down here, you have some parameters just to so you can see the comparison of what is out there and what we are doing. That the distances are of the order of giga light years compared to, of course, in the lab is of the order. The distances are of the order of meters. So then, instead of measuring um, let's say, lensing effects that are of the order of arc seconds, for us is of the order of arc minutes. The masses are of the order of the mass of the sun or much greater. And but in the lab, it is of course much smaller. The short shell radius, say, if we were to have if what we observe was created by a real gravitational lens, it would be of the order of a few microns. In the short shell radius would be of the order of a few microns, a micro black hole, for example. And here's an image of the apparatus. We start with a laser. Initially, we focused the laser to create a point source, but then later we were getting the same results if we kept the light parallel, and that made it easier for programming the SLM. So we really create a beam that is really focused at infinity, and then the SLM produces the uh, the phase that we need to deflect the light according to general relativity. So we do use the what do we know about general relativity to do the deflection. There's a picture of the lab, and so then the SLM, what it does is it deflects the light, and you can see the wavefront. It has this very unique uh, shape after is being deflected by gravity, and so the the phase of the SLM has a logarithmic form, and then once you do that, oh, by the way, so closer to home, one can simulate um, um, gravitational lens with a logarithmic axicon, and the stem of a wine glass is one such works as a logarithmic hexagons. You're going to see it yourself. You still have to sacrifice the glass so you can see the light through it. And And of course, in the lab, we measure a beautiful black hole, and a beautiful Einstein ring, and then the size of the Einstein ring scales according to the theory, and then it's wavelength independent as well. And okay, so we had a lot of fun doing this, and then at some point we decided, well, what about the light uh, not being um, observed as it is observed on Earth? Suppose we put some giant screen of the size of the solar system. What would we observe? And so then I put a camera right there, and then this is what we observed, which looks like a Bessel beam, right? If you've worked with Bessel beams before, that looks exactly like a Bessel beam. And and then if we change the wavelength, you can see that the radii of uh, the maxima and minima changes with wavelength, as it's the case with the Bessel beam. And so then of course, we had fun with many laser sources that we had in the lab. There's a lot of diode lasers nowadays that you can use. Anyway, and of course, as I mentioned before, uh, oops, okay, what did I do? No. As I mentioned before, we cannot observe this uh, with electromagnetic waves, again, because of the um, coherence challenges. And and but and also the other thing is, if we want to see it, even if we have the uh, the coherence, we need to just put a camera out there without focusing it with a telescope. So that's another challenge, is that the telescopes themselves average out uh, the fringes because they're of the size approximately of the size of the wavelength. Gravitational waves will make things a little different. Okay, so what about the diffraction pattern? Say analytically, let me look at the time. Okay, all right, and so then using the diffraction integral, one can work this out, and you get that the function that explains the pattern that we get is a confluence hypergeometric function, and turns out that we almost reinvented the wheel, because we figured out the programming of the SLM. Took a little bit to figure that out, and then to get to this expression, only to find out that that had been figured out before, because this work had been worked previously. Uh, and in particular, this function can be approximated to a Bessel function. And then the authors of this were Bliak and Minarov in 1975. And the last name might look a little familiar. Well, it is a case of a small world in physics. This Bliak is our dear colleague Kostya's grandfather. And when we compare our measurements with these theoretical predictions, we get very nice agreement. Of course, we work with complex light, so we can easily put in um, um, an optical vortex, and in fact, uh, this has been measured not by imaging, but by looking at the OIM spectrum of the light lensed by a black hole in M87. Uh, the um, a Kerr black hole, which is a rotating black hole, is produces a drag in the space time that imparts angular momentum to the light. So now when the lens is asymmetric, uh, and then we modeled this with just making um, the phase of the SLM asymmetric, and then we introduce this factor here, E. So when E is 1, it is perfectly symmetric, so we get our pistol beam. But as soon as we introduce the smallest amount of ellipticity, it kind of breaks the symmetry, and you start to get the pattern that you see as we increase. We see the creation of a caustic, and then we heard Michael Berry earlier talk about caustics of light. In fact, they're the same caustics. And then, of course, this was studied by Berry previously, and Nye and Upstill, and then there are same caustics, which are singularities of rays that we see in our bottom of our coffee cup or in the rainbow, um, where the kind of the smooth curve surfaces are folds, and then you see they end in a cusp. And um, now the caustics are achromatic, but the diffraction is chromatic. So if we were to just change the wavelength, uh, we can see, and um, in this case, my student was also changing the mass of, let me think about this. He was changing the mass of the lens. And anyway, so you can see how the different, you see a pattern, but then the maxima and minima are not exactly at the same place for the different wavelengths. Okay. So, and then when there's imperfect alignment, okay, let's see the time. Okay, when there's imperfect alignment, then one doesn't see the Einstein ring, you see arcs, and then this was first predicted by Eddington, and you can think that you can understand this just using Fermat's principle. If we have perfect alignment, the path that the light takes is a minimum in the time. They say it's um, the arrival time is a stationary point. In the case of perfect alignment, is a circle, and in the case of non-perfect alignment, you have a saddle and also a minimum, and then you get arcs, and then that's the picture of the first um, uh, gravitational lensing event, although that was not the picture that was taken, but this was a picture was taken later. But that was the first lensing observation was in 1979. And of course, in the lab, we can see the arcs just by slightly uh, misaligning the apparatus. Okay. And right. So we did that. And so then the next uh, thing was, when we see all these um, diffraction patterns, and we would like to make a more quantitative uh, investigation. And that's where our colleagues from Barcelona came into the picture. And so then the next case that could be studied analytically or computationally is the case of a binary lens. Let me say that there's also a possibility that could be observed, because you may have uh, um, a source that is far away, I mean, far away from the Milky Way, but then in the Milky Way, you have about a third of the stars in the Milky Way are binary stars. So one could in principle see that the gravitational diffraction from a binary system, and then there you have a, graph of the situation. And what is interesting is, as Michael Berry showed earlier, the pattern has a particular shape described by the singularities of rays, which is the acoustic, but it is modulated by the wave aspect of the light. And then the acoustic part was worked out by Schneider and Webb in 1986, and Michael Berry also did a very nice study of binary lensing in 2021. And so, okay, so we set up our SLM, and there's our binary lens, the phase, and then we start changing the separation between the two objects, and as soon as the separation um, is not zero, immediately we get a breaking of this symmetric pattern to produce to see a caustic, and this caustic this pattern actually goes to a very striking evolution, as you will see. So here I'm showing not the exact separation, but a scaled separation. So this is d divided by this uh, um, quantity, which actually is the Einstein radius. Um, as if it were a point source, we would see an Einstein ring. So that the radius of that ring is this quantity here, square root of 2x Schwarzschild radius, and z is the distance. And as we increase this d, we get this metamorphosis of um, patterns, which have been predicted before. Uh, and so it was quite satisfying to see that the results match previous um, work. And but now, as this D goes further than what I've shown here, then you can see that okay, in the metamorphosis you see an asteroid, and then not seen here are it is a little deltoid on the top and the bottom that are off our camera, and then here, as we increase this deltoid kind of merges in with the central asteroid, and then it becomes like a hypocycloid, and you get a fold here. And then as we keep increasing d, then now the hypocycloid starts stretching in the other direction, and then this is this connection, this theta connection, actually uh, uh, um, disappears. And as we increase d, uh, you you get just those that deltoid uh, both separate from each other. Just here, this is the just to give you uh, um, an idea of the scale of the pattern as we measure it. Okay, so with our colleagues from Barcelona, we decided, okay, let's do this this quantitative uh, comparison. So the idea was, then let's measure the caustics, and so then you have the distance from cusp to cusp in this direction, that's L1, and then the distance from fold to fold, that'll be S1, and then this cusp. Anyway, so we quantified the different parts of the caustic, and then do a measurement. And now here's what I thought was just striking, was that our colleagues are calculating. Okay, so this is the the d that we use here is a distance scaled to the Einstein radius, as I said, and which is square root of Rs and Z, as I showed earlier. But the on one end, uh, the our colleagues calculated for an astrophysical situation. So there's a Schwarzschild radius of um, um, a lens with solar-sized masses, and then, so this is the Schwarzschild radius, a scale to 1 kilometer, and then the distance of the order of kiloparsec, uh, and it's about 3 light years. A parsec is about 3 light years, and then, but in the experiment, our scale Einstein radius has a Schwarzschild radius of the order of micrometers and Z of the order of 1 centimeter, because that's the scale of our experiment. And so then here in this graph, you see this comparison and just agreement is just amazing, I thought. And anyway, so and then other things that we did was to study the um, as much as we could do was to change the wavelength of the light, and you could see that the caustic remains stable, but that diffraction pattern within is changes as expected. Um, and so then the next thing that we did was, okay, so now let's compare uh, quantitatively those interference uh, maxima and minima, and our colleagues they came up with a model. I can't really explain the model um, well, so I'll just show the results. Uh, so here is one experimental measurement. So then what we did was to draw a line, vertical line here and a vertical line here, and then just measure the intensity along those lines. And then, oh, and then there's a third line. And then our colleagues, that's what they predicted, which looks pretty amazingly similar. And so we did the same. And so my student, in trying to quantify, in trying to kind of have these two patterns overlap, um, uh, he found the maxima of um, of the theory and matched to the one of the experiment. And so there is that adjustment. And then here are the cuts for the theory and the experiment. Now the amplitudes differ. Okay, my colleagues are very concerned about that. I'm not as concerned because the experiment has a lot of imperfections. And but what I find very interesting is that once we get the scale right, the agreement is very good. And you can see it here. This is for the middle one. This one here is for this one here. But you can see here the cut goes outside the caustic, so you can see that this side is, the agreement is not very good. Uh, Let me just say one other thing, and that is that in our experiments, we saw the caustics, we saw these bright fringes, and then we saw these additional fringes. And I thought that, well, because uh, creating the pattern, the beam and the pattern involves uh, producing a diffracted beam, and then sometimes there's contamination from other diffractive orders that one has to play tricks with. Uh, that those might be caused by some of the imperfections of our diffraction, but turns out that they are also present in the theoretical simulation. So these interferences that one sees on the outside are real, which is kind of interesting. And then we have, I'll show you one other example of this comparison, but But we've done many other cases of different shapes, and then the comparison is really interesting. Okay. And so then another case with a higher density of interferences shown here, and then you can see when for the three cuts, once the scale is done, the agreement is very nice. Okay, so now is there a possibility of seeing any of this? Well, perhaps gravitational waves can reveal gravitational lensing from binary stars. So how would that happen? Like I said earlier, there's a lot of binary stars in the Milky Way, and oh, they came in the wrong order. Okay, I wanted to show the left side first. Okay, so here you have the pattern, but as it turns out, the size of the pattern, this pattern is very nice and wholesome when the this d hat, the scaled separation, is of the order one, but one is the Einstein radius, and the Einstein radius for such a vast distance for us is of the size of the solar system. So even if we do have gravitational waves coming towards us lensed, the Earth is going to be just one point in here, just a pixel. Okay, but there is a dynamic aspect of that because, and that's on the right side. This is I took this images uh, um, from the article on the first report of gravitational wave detection of black hole merger, and but they had this very nice figure that shows that as the two masses are going around each other, losing energy because they're radiating, then they start going faster and faster, and then until they coalesce. So then the light, not light, the gravitational waves go change. The wavelength changes. There's a frequency chirp, and then well, you may have heard, you can't hear it. You hook up to the website of those of gravitational waves. They've converted the frequency into audio, and you can hear this chirp. And so what will happen is that the as the gravitational waves diffracted by binary system reach us, the because the frequency changes, the pattern is going to change. The size of the interferences is going to vary. Here we have something that I did in order to change the distance of of the maxima, although in doing so, I also changed the size of the caustic. There's a way to keep that size constant, but we're working on that. And so it makes it for a very interesting um, situation potentially coming up, that this chirp that is measured might be modulated by all these maxima and minima sweeping by the observatories as they measure the gravitational waves. Okay, there's something else, and I have to admit that I learned of this just recently, and that is that once the once the merger occurs, the final black hole is a Kerr black hole. It's rotating. Of course, the angular momentum is conserved, and I was always picturing the gravitational wave coming, say, gravitational, the pattern edge on would give us a nice gravitational wave, but uh, perpendicular to the plane, as it is shown in pictures, I think the gravitational waves might carry OM. I don't know how to calculate that, but just a thought. So at some point, we also played with OAM, and let me look at time. Yeah, uh, uh, and so we didn't do that, but what we did was to add OAM to the binary uh, um, lenses. In this case, the figure shown here, they had L equals 10, the same sign of L. So when D is 0, we see a Bessel beam, which has an L equals 10 singularity in the middle. But as soon as we start separating the two masses, you get an ellipse, and then you get a very interesting caustic. So there's more there as well. So, okay, so I'm reaching the end. I want to do, okay, so I have, okay, maybe I can do two more slides before we finish. Uh, and that is that, okay, we're used to Gaussian beams, okay? And we produce them with a laser and focus them. We can generate modes, the Gaussian modes, and we also have non-diffractive uh, beams that we can generate using, for example, an hexagon. And well, you have non-diffracting patterns, but they're finite because of the previous speaker. The beam is not infinite. Uh, what about with uh, the beams generated by gravitational lensing? And I didn't have a better name to give them, but Einstein beams, right? But uh, and what is interesting is that locally they look like a Bessel pattern because they're formed by approximately parallel rays. That's my simple-minded way of looking at it. But but the thing is that since these rays get deflected less and less as you go to the outside, the beam extends. And in fact, the radius goes as the square root of the distance. So you have a beam that deflects less than what you would get with a Gaussian beam. And then this is my two students that were doing this at a time. Now this is a couple of years old. And then we send one of these beams out the hallway, and then with mirrors. And then there's a kind of a big building. So we send the light 99 meters inside indoors, and then there's the final beam. And and uh, um, anyway, we could see that the pattern is preserved 99 meters away. Okay, and now we could also indulge and say, well, what about we could not think get attached too much to uh, gravitational lensing. If we change, instead of n, the exponent of r being 1, we make some other number, what do we get? And you get a similar type of patterns. So you could think of of other types of beams that we can create this way, that we call Einstein beams. So finally, some final thoughts. Gravitational lensing has inspired a new form of laboratory astrophysics with complex light, in which to study gravitational diffraction and other lensing effects, which cannot be observed due to coherence challenges. And then we found that this diffraction by binary lenses is very rich in structure, and it may inform the diffraction of gravitation, lensing diffraction of gravitational waves in one way or another. And then there's these LIGO type observatories. And then in 1935, I guess a little bit farther down the road from us, is LISA, a space-based gravitational wave observatory. So in the horizon for doing more fun things, is to image black holes and other interesting phenomena. You have this very peculiar situation that in a black hole you have the deflection like the one we see now, but then also when you're getting very close to the event horizon, you have that the light can go around many times and then come back out. And then when the light goes around at least once, you create this fine ring that's called the photon sphere. And then so we have started working on doing that, but anyway, it's a work in progress, but looks like a very fun project. And with that, I thank you for your attention, and I thank the organizers for organizing this great conference.
Okay, thank you so much for very nice presentation, and the talk is open for questions. Okay. Any questions?
Yes, I have a comment, if that's okay.
Of course.
It's Michael Berry.
Yes.
Kiko, thank you for a very nice talk. This idea of simulating is very attractive. But as you say, the parameters, the relevant quantities vary so much, so strongly in astronomical applications that you can't really simulate what you would see with the realistic parameters. In the paper that you kindly mentioned from 2021, I estimated the different scaling laws of the sizes of fringes that you would see near different aspects of the caustic from a binary star. And I've never encountered any problem in physics where the numerics varied over such an enormous range of values, because you have the following: you have the wavelength, you have the separation of the two stars in the binary, you have the Schwarzschild radius of each one of them, you have the distance from us to the lens, and you have the distance from the lens to the source. And these are enormously variable quantities. And if you look at different aspects of the caustic near the different cusps in different parts of the caustic, sideways from the cusp, longitudinal for the cusp, and across the fold caustics, you have a huge range of physical sizes over which you would expect to see these effects. And you indeed mentioned the Earth being 1 pixel. I mean, that's a special case of that. Now, to my knowledge, and this now is several years old, I don't think that diffraction effects have been unambiguously detected in gravitational lensing. Now, if they are, they would, as you also pointed out, be chromatic, because the geometrical optics is achromatic. So the signal would be that the image of a source that's undergone gravitational lensing would be, the spectrum would be distorted. And that would be a signal that you're seeing diffraction in gravitational lensing. It could be that it's been seen already, but discarded because of the geometrical optics idea that the spectrum should be the same apart from redshifts and the like. Now, the places where you would most strongly see these effects would be near caustics, because near caustics, everything is not only more intense, but the sizes of the fringes are scaled differently with the wavelength, as I mentioned earlier. So it would be near caustics that one would look for distortion of the spectrum of the source. Now, my question to you is, you obviously know the literature better than I do now. Do you know of any unambiguous observations of diffraction in gravitational lensing?
Oh, thank you very much for your comment. And I don't know. I haven't read, and the other Okay, so I think what could be observed, I would think that in microlensing, one might be able to observe something, because otherwise, in other observations, like the ones of the Hubble, the telescope does a lot of averaging, because it averages all the fringes. But I'm thinking that perhaps in microlensing there might be something there that people may not have considered. I haven't read it.
Okay, thank you.
Okay, I see one more hand raised. Please.
Hi. Hi, Kiko. It's Albert speaking. Um, just I want to know if I really pick it up. Do you think your experiment can also tell you something about the nature of gravitational waves? Because you are talking about gravitational lensing, but they can also give some information about the way gravitational waves are detected, or is something completely different?
Well, if I mean, the diffraction pattern could reveal the source as much as the lens itself, but those two are somewhat convoluted. But I wouldn't think. What do you mean? But well, suppose that we're thinking gravitational waves, and we think of a merger, then it is possible that the gravitational waves come already with OAM, and I'm not sure if that has been considered, but
So my comment comes from the different nature of gravitational waves and electromagnetic waves, because the gravitational wave, it's a tensor wave, right? It has different polarization properties, so to say, because it has like quadruple, polarization, something like that. When you couple to light, I don't know, is this, I'm ignoring this. So it's just, do you think there is a way of you can somehow pick up some information about this particular feature of gravitational wave?
yeah, I have not considered that, but yeah. So all these studies, it's just scalar, but I assume polarization plays an important role. Yeah, yeah, I don't know. I can't answer that question.
Okay, sorry. Sorry about
Oh,
this.
great to see you.
Okay, if there is, let me check if there is no other questions, it looks like. Let's thank Kiko again and move to the next talk. So the next talk is titled Polarization, Energy Flow, Angular Momentum of an Electromagnetic Waves.
Thank you. Can you see my presentation?
Yes, yes.
Okay. This is the title of our report, and these are my co-authors. First of all, maybe a trivial introduction. I will begin our report with a quote from a source that most of you probably know from school days, namely from the Feynman lectures of physics. According to Feynman, there are only three conservation laws involving space and time, namely the law of conservation of energy, of momentum, and the angular momentum. These laws being determine the basic characteristics of any physical systems. Here, we will not talk about other equally important conservation laws, for example, the law of conservation of charge and other similar laws, since they are not directly related to time and space. A rather trivial conclusion follows from this statement. If we exclude mass, then the main characteristics of any physical systems are, first of all, energy, momentum, and angular momentum. If we are to be consistent, then from the last statement, it follows that all other characteristics that we use to describe the behavior of a physical systems are in some sense derivatives, characteristics of energy, momentum, and angular momentum, or at least are determined by them. That is why we can assume that it's precisely the consideration of the transformation of energy flows, momentum, angular momentum, that can carry more information than the characteristics obtained by conventional optical methods. It should be noted that such quantities as momentum and angular momentum of a wave, if one way or another, related to energy flows, in other words, parameters of the Poynting vector. Their specificity, structure, this, for example, this article. The purpose of this report is to illustrate the above statement and to some extent outline approaches to development of so-called energy formalism, the formalization of calculation of the characteristics of energy flows and the measurement of their parameters. We will demonstrate that our reasoning is at least somewhat valid using the example of such a phenomenon as polarization. In the most general sense, the essence of wave polarization is that the end of the field strength vector moves along a deterministic trajectory in time. It's well known that for a coherent wave, this is an ellipse. By default, it assumes that nothing fundamentally changes when one analyzes a polychromatic wave. First of all, we will point out some situation when fundamental, well-known, widely used polarization characteristics don't quite adequately describe the behavior of the strange vector. Let us consider the behavior of the end of the field strength vector for a wave formed by two orthogonally circularly polarized coherent waves of different frequencies. According to our general definition, such wave is polarized. The Stokes parameter of such superpositions can be written as here. If the moduli of the amplitude of the wave are the same, then this parameter is equal to 0 also. According to classical concepts, such resulting wave is depolarized, which generally speaking is not the case. Note that this not the only one case of contradiction between the classical description of wave polarization and the real situation. The question arises, what do the zero values of the Stokes parameters indicate? As it is well known for a monochromatic waves, the inhomogeneity of four Stokes parameters determines the spin energy flows and, as a consequence, the spin angular momentum. Transverse components of the spin components of a polychromatic wave are defined by these relations. Then, zero value of the fourth Stokes parameter indicates that such a superposition has zero spin angular momentum. Is from this statement, the quite logical to conclude that in general, the Stokes parameters of a polychromatic space cannot be used to describe the polarization state of wave. However, these parameters are uniquely related with magnitude of the spin angular momentum of the wave. Let us know another well-known fact. When we have the uniformly polarized wave, which passes through some physical system, we use such procedure. The trivial conclusion follows from these notations. The intensities of intensity of wave, output wave, does not depend from the polarizations. But in the case of transformation of energy flows, the situation is completely different. Let us try to illustrate this fact by a fairly simple example. It's well-known pattern. The energy flows in the area of the center of the Gaussian beam and the vortex one. It can be seen that such energy flows are practically identical in both cases. Such similarity, in our opinion, must lead to the similar transformation of energy flows when such beams passes through the same system. Let us demonstrate this fact by using the example of diffraction of such beams at the edge of the screen. It's known that during diffraction of vortex beams at the edge of a screen, in the far zone, the vortex center, coinciding with P singularity, is shifted by an amount that depends only on the degree of beam overlap. The direction of the shift is determined by the sign of the topological charge of the vortex. It has the direction of circulation of energy flows in the input plane. Energy flows are transformed similarly if a circularly polarized Gaussian beams diffracts on the screen. The magnitude of P singularity shift is the same as in the previous case for the same degrees of overlap of the initial beam, and the direction of its shift is also determined by the direction of circulation of energy flows in the input plane. In our case, by the sign of handedness factor, right or left polarization. Note, the intensity distribution is symmetrical relatively to the beam center. In other words, is it's the structure of energy flows that indicates the nature of polarization of the initial beam. The shift of the P singularity can be interpreted in the terms of interaction between intrinsic vortex circular polarization and extrinsic transverse intensity displacement degrees of freedom of the light beam, so-called spin-orbit interaction. Note, for the circularly polarized Gaussian beam, orbital component is zero in plane before the screen. The non-zero orbital component of the Poynting vector appears only after passing the screen. This occurs to the fact that some phase gradient emerges in diffraction fields. As follows from the figure, the phase change occurs only in one direction, perpendicular to the edge of the screen. And the second, the change itself in the zone of the diffracted beam is small and it's practically linear. To explain the appearance of the Poynting singularity shifts, let us turn to this figure, which shows the parameters of a resulting Poynting vector, its spin part, and the orbital part. As follows from the figure B, the spin part is symmetrical circulation of the vector, while for the orbital component, figure C, the transverse component is directed in one direction at any point of the field. Accordingly, in the upper part of the field, the spin and orbital components in the same directions, and in the low part they are oriented in opposite directions. Since the equality this relation, then the modulus of the total transverse Poynting vector in the upper part is obviously greater than in low part. Which leads to a shift of the 0 point of the transverse Poynting component. The data of numerical modeling were confirmed experimentally. The bottom row of the figure corresponds to the distributions of the parameters of the reconstructed transverse component of the Poynting vector. The parameters were reconstructed using method described in this article. Based on the obtained result, it's obvious that when one considers the propagation of beams with angular momentum through any physical system, regardless whether its momentum orbital or spin, the transformation of energy flows is performed in a specific way, unlike the propagation of wave in which such angular momenta are absent or insignificant. It's obvious that such behavior of the wave is caused by the action of the conservation law of angular momentum. Let us demonstrate this statement with result of another experiment, the essence of which is the following. Let us assume that a Gaussian linearly polarized beam propagates through a single mode fiber, and then the similar but circularly polarized beams propagate through the same fiber. The elements 5, 11, 10, N15 form an interferometer so that at the output of the arrangement it is possible to observe the corresponding interference pattern. Element 8 is a shifting device that allows the fiber to be moved during the interference measurements. Obviously, ideally, if a linearly polarized beam passes through a single mode fiber, then when the fiber is shifted at the output of the arrangement, the phase relationships in the beam should not change and the interference pattern should remain stationary. In contrast to the situations, the movement of the fiber during the passage of circularly polarized beam due to the action of the conservation law of angular momentum should lead to some phase changing at the output of the region. The interference pattern should at least shift. Obviously, such changes become really noticeable during the start and stop of the movement. Is to this moment that maximum attention was avoided. Unfortunately, in our experiment, we used a standard single mode fiber used in the communication. As it is known, the cutoff wavelength of such fiber is about 1.2 micrometers. For shorter wavelengths, including the red wavelength of our laser, such fiber becomes multimode. As a result, when the fiber was shifted, a change in the phase relationships was observed in the wave passes through the fiber, even if it was linearly polarized. This is due to the fact that when bending such a fiber, it's impossible to avoid interaction between the fiber modes, and as a consequence, the transfer of energy from one mode to another. In other words, the interference pattern is unstable in both cases. However, the presence of angular momentum in a circularly polarized beam should lead to field changes somewhat different from those in linearly polarized beam. Unfortunately, given our experimental condition, it was possible to make only qualitative estimates. As we can see, the interference pattern is destroyed in both cases. However, for a circularly polarized beams, it destroyed more slowly. This figure shows the moments of maximum transformation of interference pattern. As we can see, for a linearly polarized beam, the visibility of pattern drops almost to zero, while to a circularly polarized beam, it's preserved at least the phase relationships change less than for a linearly polarized beam. Thus, we can state measurements of traditional waves characteristics, for example, intensity, polarization characteristic, don't give a complete information of changes in the field of wave of general kind when it passes through a certain physical system. For example, the process of transformation of an elliptically polarized beam during diffraction of a wave at the edge of a screen. The second, the most complete information of wave transformation obviously comes from the analysis of its energy characteristics, in other words, distribution of the Poynting vector characteristics. In this regard, the following question arises. There I need to develop an energy formalism that allows us to relate the input and output energy parameters based on certain relationships. In this aspect, we don't yet see any other way now than using traditional approaches, including calculation the output field and then moving on to the characteristic of the pointing vector. We add that this approaches ensures the calculation of the pointing vector parameters not only in the coherent but also in the polychromatic case. To use the energy approach to the analysis of the optical fields, it's necessary to develop new reliable methods for measuring or restoring the pointing vector parameters. If we talk about the paraxial approximation, then in this part we can consider such a problem solved. Indeed, one of the possible expressions of the transverse component of the pointing vector has these forms. Based on such notation, it's possible to measure the components of the pointing vector transverse energy flows using full phase symmetry and the field of the field components and the local Stokes polarimetry. It was on the basis of this method that the characteristic of pointing vector was restored for the diffraction of acicularly polarized beams at the edge of the screen. However, it should be noted that the phase symmetry of the components is not a simple task, which involves analysis and restoration of the spatial phase distribution, vibration stabilization of the experimental setup, and the need to form a reference beams. At the same time, in this relation, orbital part includes not the phases themselves, but the derivatives. They can be measured directly by analyzing Hartmanograms obtaining using a micro-length metric. Therefore, the following scheme can be used as the basis for a device that allows one to obtain the characteristic of pointing vector directly at the output of device. A certain field is analyzed, polarization insensitive splitter divides the wave into channels. Measurements are performed for identical fields here and here. This polarizer selects the X and Y component, which make it possible to analyze the corresponding intensity distribution when this quarter wave plate is absent. Simultaneously, in this channel, the using of the matrix length allow us to obtain the local distribution of phase derivatives for X and Y components. The introduction of the corresponding oriented quarter wave plane allow us to obtain the corresponding Stokes parameters. I hope that this device will be implemented and tested in the near future with the help of our colleagues from Kyiv University. In this context, prospects of the Poynting vector measurements can be mentioned that follow from the existence of large dielectric particles with almost dipolar regimes of miscaterings. A dipole particle located in an optical field experiences a mechanical effect of force, which is described by the following expressions. The equation 8 for mixed force included the term which is proportional to the Poynting vector. And as it is seen, for some conditions, the Poynting vector characteristics are completely defined by this force, and this opens new possibilities for the Poynting vector registration using special probe particles. In conclusion of the report, I would like to note that despite the fact that it's traditionally believed that polarization methods and the characteristic obtained with their help carry the most complete information about the field. It's necessary to state that traditional polarization parameters don't always adequately describe the wave transformation. In addition, the transformation of energy flow in vector fields, even uniformly polarized, is fundamentally different from a similar situation in scalar ones. That is why, in our opinion, the development of energy approaches to the analysis of optical fields has good prospects in both fundamental and applied aspects. Thank you for your attention.
Thank you very much for very interesting talk, and the talk is open for questions. Okay, let's see. Let's see in hands. Okay, while everybody thinking about questions, let me ask a quick question. It was very interesting to see the predictions that in circularly polarized light and linearly polarized light propagated in a fiber should show different interference pattern or dynamics of interference pattern. And I understood that you kind of have a mode coupling which doesn't allow observation of this effect. But have you tried to do it in numerical simulations with like truly single mode fiber?
Thank you for the questions. This is a recent result, and we cannot do some theoretical consideration of this process, only experimental results.
I see. Thank you. Hey, any questions? If I don't see your hand raised, please just unmute yourself and ask question. Okay, well, if no questions, let's thank the speaker again, and we'll move to the next talk, which, oops, let me open the brochure. I'm not sure. Oops, sorry, I'm not sure what my computer is doing. Just 1 second. Open the talk. Okay, here it is. Okay, next talk is titled Dynamic Control of Spatial Coherence Aware Superposition of Vortex Lattices. And this is a collaboration between Poland and Mexico.
Yeah. All right, I'll try to share my screen. Do you see my slides?
Yep.
All right, great. Thank you. First, I'd like to thank you for the invitation and thank you for putting an effort to continue with the coherence that we have been participating for several years. And I keep my fingers crossed that the online format is temporary and we're gonna see each other in person very soon. This talk would be about transverse spatial coherence. So all of the coherence aspect that I'm gonna talk about would relate to the correlation between 2 points in space at fixed time in the transverse plane. So the question is how does spatial coherence be modified? So typically what we would like to do is to start with the coherent and go to partially coherent or non-coherent, depending on the application. And there are a few categories we can think about. The most obvious is to use von Caesar-Zernicke theorem. Later, not so obvious are increased number of spatial modes, incoherent mixture of modes, or random modes representation. And all of them are to modify the coherence to obtain partially coherent. So let me briefly go through all of them and show you some experimental examples of each category. The first most obvious is to use rotating ground glass diffuser, where the coherence can be controlled by the grid of the diffuser, and most importantly, however, is the size of the beam at the diffuser. And this is a nice work presenting a tutorial how to implement that experimentally. But this is not the only solution. We can think about different approaches. We can use digital micromirror devices to steer the beam across the diffuser that is not rotating. We can also go into more complex coherence structures by playing with the complex amplitude of the illuminating beam, or come up with another solution for the grid to implement various patterns. So all of them would be this von Caesar-Zernicke theorem. Another quite popular as well is to play with the number of spatial modes. So this is a nice work where they suppress the artifacts coming from the meta holograms, where they increase number of spatial modes coming out from the laser cavity. So they moved this single lens here to go from a single spatial mode to multi-mode coming out from the laser cavity, and you can see the results here. So here we can see artifacts and lack of artifacts. And further, we can use mixture of modes, and that's a work of Miguel Alonso and other researchers, where they generate, and this work is specifically to provide a technique to measure radial coherence, but in principle what they do is display various aggregation modes with different azimuthal and in this case radial number to control this coherence and change the shape. That can be done with the SLM. And the last but not least is to still use the SLM but provide various speckle patterns on the SLM. So different random, more or less random phase patterns on the SLM and control their statistical properties to control the coherence. So today I'm gonna show you something that we came up with, which we call dynamic control of spatial coherence, but we propose to use vortex lattices. And the work would fit into the fourth category. So that would be random mode representation. And the role of random modes will be these lattices that I'm gonna talk about. And it started with the work of Gruber and Raoul some years ago, where they analyzed the behavior of the singular point under the low coherence. So with their analysis, they came up that actually we can differentiate two areas. The one area, which is this outer one, where the singular point the singularity behaves like a fluid, and the inner area area where the singular point is more concentrated, and these are just single instances of the singular point position under the low coherence. So that was the origin, but later they follow up with the experimental method to digitally generate partially coherent vortex. So that is sort of reverse engineering. So they started with defining a circle, which is this concentrated behavior of the singular point, and the circle has a fixed diameter. And what they did is they randomly selected the position of the singularity within the circle. And they do it for 500 instances. So 500 coherent summations of the randomly selected singular point, and that all goes to one hologram. So one hologram is the output of the 500 coherent summation of those fields. And they follow this scenario with the same parameters, generating 200 instances of such holograms. And what they did later is display these holograms in a loop on the spatial light modulator. So you can see the experimental results here, and this is the intensity of two cases where this is non-coherent, partially coherent, and coherent case, and the coherence is controlled. Is the transverse coherence length is given by this equation, where d is the observation distance and c is this diameter or radius in this case. Radius of the blue circle within each the vortex is randomly shifted. So you can think about that. If the circle is very small, this becomes the coherent case. If we increase the diameter of the circle, we go into the partial coherent regime. So experimental implementation is quite simple. The expanded laser beam, which is this here neon laser, illuminates the SLM, and in a loop we display these holograms, filter the beam and the first order of diffraction that goes into the interferometer with two Dove prisms. The role of Dove prism is to provide the interference between a field and its counterpart to obtain the interference fringes that we can later analyze and get the complex coherence function, the cross correlation function. So we repeat their experiment, and we can confirm that the paper is nicely written. It's easy to reproduce. So the bottom is the experimental result. The top are our results. However, this generates partially coherent. It does not shape the coherence of any illuminating beam. So it works for Lagrangian modes. And obviously it works as well for the Hermite Gaussian, and these are our results because they're very similar, and the Hermite Gaussian can be created as a superposition of Lagrangian Gaussian. So all of those beams that have this behavior that the lack of coherence provides a shift of this singular point will probably benefit from this method, and we can generate partially coherent beam using this method. However, it does not change the coherence of any illuminating beam. So what we propose is to go one step further, and instead of playing with a single vortex, we propose to play with vortex lattices, and that was inspiration from the work of Karen Volke, which collaborated with us on this project, and she studied vortex lattices for a few years already, published a few papers on that, and established some degrees of freedom that we can associate these lattices with. So what are these major parameters? We can think about number of vortices in a lattice, the sign of vortices, if it's the same, I'm talking about the sign of subsequent vortices or anti-correlated as in the regular spectral field, or the value of topological charge. The idea is the same. So we took the Rao's work, and we proposed to do sort of the same, but superpose lattices, not just a single vortex. And the analogy is very simple. If we reduce the lattice to just contain a single vortex, we come up to this original idea. And let me show you One instance of this field is the lattice that is consisted of n vortices, which the position of each singular point is randomly selected within a circle of a fixed diameter. And the rest remains the same. We construct the 200 holograms and display that on the special light modulator. But before that, let me show you the numerical simulation, and I'm gonna use the as a reference a nice feature that I like from the work of Toshimitsu Asakura. However, he used the rotating ground glass diffuser, and I'm using those lattices. But I see some analogies here. So in the role of the coherence draper are our lattices. And in his setup, the first prisms acted as a selector of the 2 points that will interfere at the observation plane. So what we do is we cut out the 2 points out of the field, and we cut them out and put them in a fixed distance. And this is the role of the second prism that provides the fixed angle of inclination between those two fields to have the same special frequency of interference fringes. And he changed the parameters of the ground glass diffuser or the beam diameter, and what we change are the parameters of our lattice. Here are the simulations. So you see that we scanned our lattice with this 2 aperture that is obviously a Young interferometer that is fully controllable, and obtained the interference fringes, measured the contrast, and from the contrast we take the value of the amplitude of the complex coherence function. And obviously these fields are in a loop. I'm just showing you the first instance, but it was calculated for each instance and then averaged out. Here are the results from Asakura, and here are the results from our experiment. And in the bottom, you can see the distance between the two apertures. So basically, we scan the field farther from the center. Here is the results of the simulation, where on the x-axis you have this distance between those two apertures, and on the y-axis we have number of vortices. And you see that if we increase number of vortices, the coherence drops down, and also if we go further, the coherence drops down, which is the expected behavior. We tested that in this experiment, but also we implemented another part of our setup, directly implementing this controllable Young interferometer, where we put another special light modulator, and we display these 2 circular apertures and control the separation between them. And those 2 fields go further to something that is not Sagnac interferometer. It is slightly different because this polarization beam splitter is rotated. This is on purpose, but this is our setup that provides the fixed inclination between those 2 points, no matter the distance between apertures. There's one trick that we did on the second SLM to control the alignment between those 2 selected parts of the field. This is the diffraction grating, which is mirrored for both of them, and we change this distance between apertures. So on the left you can see the simulation that I showed you before, and on the right you can see the first experimental results. So we are pretty happy with them, especially for the number of vortices up to 4, which has a good relation between simulation and experiment. This is slightly more difficult, but close enough to say that we confirmed that experimentally. Obviously, there's a lot more going on here, so we can look into this single number of vortices. So going from 0, which is fully coherent, nothing is displayed on the special light modulator, and going to 16, you can see that there's a nice tendency here. But the question is, does this method work for any type of the illuminating beam? And to check that, we introduced the vortex with this paraphase plate here, just before the SLM1, the SLM where we display our holograms to change the coherence. And now we use this setup with two dove prisms and observe the interference fringes and retrieve the cross-correlation function. And you can see the experimental results for three cases, the fully coherent part where nothing is displayed on the SLM and something that we start playing with the number of vortices going from 1 to 9 and reducing this coherence. We also look at another parameter, which is the higher topological church, and these are simulations for the same cases, but however, we change the value of the topological church of a single vortex in this lattice. And what is not surprising is that we saw this for the single case where there is a single vortex. We saw this dark area, and this dark area is visible for the topological church 1, and for from 2 you can see first one here and probably the second one here, which is more obvious for 3. We have this these 2 dark areas, and probably the next one would be farther. It's visible if we look at the logarithmic color bar. You see those dark areas that I was talking about here. And what is the cause of that? Obviously, we came back to the original work of Andrew Forbes, Raul Hernandez Aranda, and Grover Schwarzwander, this digital way to generate partially coherent Lagrangian modes, because we reduce the number of vortices to a single instance, and this is obviously the profile of the cross-correlation function. So these dark areas are number of rings here, which disappear if we increase number of vortices in a lattice. We don't see them anymore. We also verified that experimentally we have small misalignment. However, this dark area here is somewhere here, and I see that the x-axis is not in scale. However, this is close to 0.4, and so is here. So we confirmed that experimentally for higher topological charges as well. But the question is, are there any other degrees of freedom? And the most obvious case we dealt with is the uniform distribution of those vortices. So this is the simulation of, I guess, close to 1,000 of the positions that would be generated for a single vortex between the circle or many vortices if we increase number of vortices in a lattice. But you can also change this distribution, and this is the simple parameter that controls that. We can do a beam that would be probably incoherent in the center, where we increase number of vortices locally and decrease number of vortices in an outer part. So this is the whole beam that is going to be illuminated, and you see this is the line that let us switch from the fully coherent part to non-coherent. And on the right hand side you can see the experimental validation of that. So this is the same. So the y-axis makes no sense. It's just to visualize that there is a central part which was consisted of the 8 vortices in a lattice, which is bluish, so it's non-coherent, and the outer part was just for a single vortex in a lattice, which is more coherent, and this is the line that we predicted where this switch comes up. But the question is, what are the limits of the method? And to do so, we wanted to see if we have to use those variables that they did in their work, or we can go down with them. So we came up with another setup, which is much simpler, and we checked 2 things at once. So not only the parameters, but also we changed the device. So now we use digital micromirror device, which is also shaping the complex amplitude, but using binary amplitude modulation. And we put the ground glass diffuser here. However, it's not rotating. It's just to generate speckles, because we want to measure the contrast of the speckle and see how this contrast is affected by our parameters. So first of all, we changed this 500, so the number of lattices that are superposed, and we came up with the results that at least for that setup, we can go down from 500, which would be farther down here, to something that would be close to 10 10-ish, and we see that the contrast is constant, and the subsequent plots are just different number of vortices in a lattice. So actually, some of the results that I shown you are already done with the less number of lattices, which is simplifying all of the calculation. And also we changed the number of holograms to see what is the shortest time frame that we can shape the coherence. So this is what we achieved was 2 kilohertz of frequency. So within this time frame, we are able to shape the coherence that was corresponding to close to 20 number of holograms displayed in the loop. And coming slowly to an end, I showed you the way to control the spatial coherence following this random mode representation, and starting from the work of Raoul et al. And to our work and our initial analysis shows that we can also provide the equation from the transverse coherence length, which is including the topological church and number of vortices. So if there is a single topological church and single number of vortices, we come up to original Raoul equation. Single shot setup with the SLM directly measuring cross-correlation function, but also the other setup, more precise, that is this controllable Young interferometer, and capability for structuring the spatial distribution of spatial coherence. So we can think about different distributions and obviously non-uniform, non-concentric distributions as well. We did not confirm that experimentally, but in principle, that should be possible. And last but not least, I would like to thank my team that work on that, especially Przemek and Jakub, who dealt with the SLM and the experimental experience with the SLM, and Claudia and Adrian that dealt with DMD, and obviously Karen, who supported us with the analytics and the equations for vortex lattices. Thank you so much.
Okay, thank you very much for this great talk. And the talk is open for questions. Okay, any questions?
So maybe I can ask a short question. In your experimental part, what was the resolution of the digital micromirror device you were using?
Yeah, that was 2K, so that was 9020 by 1080 pixels. So typical of the shelf DMD.
Okay, and in the simulation, you perform the calculations for the same resolution, yeah?
I think that yes, that should be the same. Yeah, because we use the same. The output of the simulations are holograms that we directly upload on the SLM or DMD. Yeah, it is the same.
Okay, so that was, as I understand, the binary amplitude modulation without phase.
So no, in principle, we modulated the phase because our fields are phase fields, so we provide the phase variation. What DMD offers is the binary amplitude modulation. So there are techniques to modulate the complex amplitude using binary only modulation, and this is the simplest Lie method holography. That's how is it called, and that's what we applied. But yeah, those two devices can be used for the same purposes and provide the complex amplitude modulation, despite working only on the binary amplitude.
Well, I was interested if the binary amplitude modulation was used in the simulation, because your results contain phase information.
No, it wasn't, but I'm not sure if it's the case. I don't think that it would change the simulation at any point, because the binary is just a step to get the binary modulation is just a step to provide the complex amplitude modulation in case of DMD. And what we are able to do in the simulation is just directly work with the complex amplitude, and that's what we did.
Okay, thank you.
Thank you.
Okay, thank you. I think in the consideration of time, we'll have to move to the next talk. Thank you very much.
Thank you.
And the last talk in our session will be on magnetic field-induced enhancement of acousto-optic. Sorry, my computer is doing something. And the talk will be given by Dr. Oksana Mis.
Hello. First of all, I would like to thank you that you invite me on this meeting. My presentation is magnetic field-induced enhancement of acousto-optic diffraction efficiency. Diffraction efficiency. During my topic, I will say some word about the importance of this topic. I introduce some prerequisites of influence of optical activity on the efficiency of acousto-optic interaction. I consider a mechanism of influence of Faraday rotation on the efficiency of acousto-optic diffraction. I will show result of our simulation. I consider the case of beta barium borate crystal, KDP crystal, and natrium bismuth molybdate crystals. Some words about acousto-optic diffraction. This well-known phenomenon, which is widely used for the manipulation of the light beam, such as modulation, deflection, scanning, tunable filters, and inconsistent appearance of the diffraction grating of the refractive indices due to the elasto-optic effects. The efficiency of acousto-optic diffraction is determined the several parameters. The main of them, the coefficients of acousto-optic feature of merit. One of the important parameter is the acousto-optic feature of merit. It depends on the refractive indices, effective elasto-optic coefficients, density of materials, and acoustic wave velocities. So if you want to reach the high efficiency of acousto-optic feature of merit, we can choose the materials with high refractive indices or with low acoustical wave velocities. But if you choose low acoustic wave velocities, we will have devices with not so fast, and the problem of increasing the efficiency of acousto-optic interaction is very important.
I'm sorry, please scroll your presentation. We can't see every slides.
Yeah, and also maybe you could switch to presentation mode. I put it in the chat, but I probably couldn't see it.
Can you see my slide?
Well, it's still not in presentation mode.
We see as a set of slides, not as presentation, but as separate slides. Or you change slide one to one, or scroll, switch the presentation.
I will change. Can you see the change of the slide?
No.
We see the fifth slide.
Yeah. Yeah, now it's moving. Yeah.
Second one.
Yes.
Third one.
Yeah, now it's scrolling.
Can you see this slide?
Yes.
Theoretical background. Can you see this slide?
Yes.
Yes. Yes.
There are several methods to enhance the efficiency of acousto-optic interaction. It can be by searching new materials or developing new materials, or optimization of geometry of acousto-optic interaction when it is when we search the most effective direction propagation and propagation of optical light and acoustic waves. And one of the way enhancing of acousto-optic efficiency is searching materials with optical activity or another properties of like optical activity or Faraday rotation. One of the first, probably in the first time this phenomenon was observed, but Yanova Tanabe. And this, how the optical activity impact on the efficiency of acousto-optic interaction. When the optical light propagate in optical active media, it became elliptical polarization. The appearance of ellipticity of incident optical light results in the appearance additional components of electrical displacement vectors. And it results when if you know the components of electric, if you know the components, the displacement of which vector of displacement, and we will see that appearance of ellipticity of incident optical waves results and appearance additional components of elasto-optic tensor, and it of course results with increasing the effective elasto-optic coefficients. In the same way, when we have
I'm sorry, please change your slides. We can't see your slides.
I will click and the slide.
Yeah,
you don't switch your presentation. You need to switch it.
Yeah, we still see a theoretical background slide. Yeah, now it's switched to another one. Yeah, now we can see slide number 5.
In the slide, I will talk about that appearance ellipticity of incident optical light result in appearance additional components of electric displacement vector, and it will result in the change of value of effective elasto-optic coefficients. Can you see another slide?
No, not yet. Oh, now it's 7. Maybe if you switch to presentation mode, then it will be working better.
I will try to switch by using my mouse, but it doesn't work. Seem to be. And
Can you try like on the bottom of your screen? There are like little windows where you can switch to like full screen mode. Can you see it? Yeah, so it's basically like 4 little squares, then something else, and then one kind of screen looking icon. So you can click on it and that would be full screen. Like at the very bottom right of your screen of PowerPoint.
Нажмите клавишу F5. Будь ласка, можливо.
Yeah, that would be.
Can you see?
Well, we can see it, but still in like non-presentation mode. But that's okay. Let's just continue, and maybe you could switch slides on the left panel. So.
One moment. Can you see?
Oh, it's still the same.
Can you see?
Yeah, but it's still the same. Slide number 7.
7.
Maybe I will try some words, but I don't want to waste time, and we study the BBO crystals, KDP crystals, and we obtain that application of magnetic fields leads to the sharp increasing of the efficiency of acousto-optic interaction, caused by the appearance to the additional, it's caused by the increasing of effective elasto-optic coefficients, and which is resulting in appearance in ellipticity of incident optical wave due to the action of magnetic fields. And we investigate the isotropic and anisotropic diffractions, and in both cases we obtain the increasing the efficiency of acousto-optic diffraction, and we can state that application of magnetic fields allow us operate the efficiency of acousto-optic diffraction and operate the acousto-optic diffraction. Thank you.
Okay, thank you very much. And any questions? So what type of crystals have you studied?
It was uniaxial crystals, BBO crystals, KDP crystals, and not-resistant molybdate crystals. It is crystals without initial optical activities. So the change of effective elasto-optic coefficient will caused only by action of magnetic fields.
And how strong magnetic field is needed for this effect?
We did not make an experience, and from our mathematical simulation, it's 1 or 2 kilostat.
Thank you. Any other questions in the audience?
No. No, thank you very much.
Yeah.
Thank you for your management of this session. Thus, we finish our session. It was the last talk. Now we have poster session. It begins now, 4:30. And tomorrow we have 4 parallel sessions, 1 and 3, 2 and 4. Please take it into consideration, and every session has its own link. Please take it. Thank you very much. Thank you for your participation. Thank you. Have a nice evening or day. See you tomorrow. Goodbye.
Bye.